morning, here we are once again. It's the video lecture for Physics 2A, video lecture 6. And I had some requests for a couple of problems, so I'll start by working some problems at the board. And I intend to do this from now on, things that have already been turned in generally. So homework problems that I'll do at the beginning of today's lecture are Chapter 1, Problem 1, and Chapter 1, Problem 1, Chapter 2, Problem 2, Chapter 2, Problem 4. So the first of those problems was a dimensional analysis problem, and I'll show you this formula here. Capital T equals 2 pi square root of L divided by G. This is the period of the simple pendulum that we'll actually bring into play later this semester. Towards the end of the semester, we'll do this whole thing systematically. Period of the simple pendulum, but I may as well show you what's being discussed here. If you put a little object at the end of a string and let it swing back and forth, small initial angles, then the time it takes to go over and return again is called the period of oscillation, and this is how much time it takes. In the meantime, we've learned about this letter G, so this won't be difficult. We're asking for show that that this is dimensionally consistent. So to show that this is dimensionally consistent, what we could do is square the whole thing, and we would have T squared equals 4 pi squared L divided by G, and we know all of these quantities now, don't we? So the next thing is to ask what are the units, and we know on the left side we have seconds squared, period in seconds squared. 4 pi is dimensionless, L is meters, and G is meters per second squared. The meters are going to cancel. Flip that one there, you get seconds squared. Done. So this is a great lesson. All physics equations must be dimensionally consistent, or else they are not real equations. Okay? If the dimensions aren't right, the equal sign is not true. Good. So now let's look at the other two problems. So chapter 2, problem 2 was something about the speed of light. How many miles does a pulse of light travel in a certain time? So here's what we're going to do. We have our definition of speed. Speed and velocity not interchangeable, but we're going to learn the difference as we go along. So we have delta x over delta t, okay, and meters per second, miles per hour, what have you. So let's see what they asked us. How many miles does a pulse of light travel in a certain amount of time? Well, we're solving for the distance, so the distance equals v delta t, and now we learn that we have 3 times 10 to the 8 meters per second. That's the speed of light, and our little increment of time was just 0.1 seconds. 0.1 seconds. We see we get the cancellation in the units, and that's 3 times 10 to the 7 meters. Now, I'm not big on conversions in the sense of I don't do them in class. We have everything in terms of meters per second and we're fine. Now, if you do have to convert miles and that type of thing, you can look at the beginning of your book, and we have 1 mile equals 1,609 kilometers, or 1 mile equals 1,000 1,609 meters. Okay. Did I say kilometers? 1.609 kilometers, 1,609 meters. So that's what you do is you make a conversion then, or since we have meters here, we want to convert to miles, we would just actually plug in the meters and get the miles. But you always just use these definitions to make your conversion. And again, if you wanted to compare this to the radius of the Earth, radius of Earth equals 6.38 times 10 to the 6 meters, okay? And then you can make the comparison between these two numbers. You see, of course, scientific notation is really important because that immediately gives you a handle on the relative sizes here. Good, so we have that. So what, this was 2, problem 2. And the last one addresses the difference between speed and velocity. So this one's useful for us to talk about. So speed is distance per unit time. Velocity is displacement per time, and so there's a difference. So this is chapter 2, problem 4, and the question is, football player runs from his own goal line to the opposing team's goal line, returning to the 50-yard line, all in 18 seconds. So here's a good one for a number line, and we've got 50 and 100 yards. Okay. And so he starts here, A, turns around and ends up here. So the speed, I'll write speed here, is that he's covered 150 yards. 150 yards in 18 seconds. Okay, you do the rest. The velocity is the displacement over time. And the thing about the displacement is, I'll use a different color, it's just from here to there. It doesn't matter that he went to the 100 and came back again. His displacement is 50 yards in the positive direction. So that's 50 yards, 18 seconds, and it's really in the positive direction. We'll be talking about vectors very soon, and then we'll see that this positive sign plays a role. Here it was trivial, but in general, displacements can have a positive or negative sign on them. Good, so those are the homework problems that people were interested in discussing. And now we're going to go back to the matter at hand. So we're wrapping up chapter 2. Okay, we've done motion with constant acceleration, and we've done some free fall problems, and I assigned some free fall problems that I'll talk about later. So generally I'll do these homework problems at the board after they've been turned in. Okay, in my classes, when I have a group here in this room, I usually have the homework turned in the following day, and then I immediately begin the hour with homework problems, and people have it fresh in their mind. Okay, but because the way we're doing it, we have to put a 1 week space between it. Okay, so let's go to constant acceleration kinematics and say a little more about that. This time I'm only going to write the formulas down with the acceleration, and if we do a free fall example, we'll put the G in on the spot. Okay, so this is kinematics with acceleration is constant, and I can put these formulas up here once and for all. We will have x equals x0 b0t 1/2 a t squared. Always make sure you put the a in the numerator. So I'll actually put this as a note here. What this means is a divided by 2t squared, not what some people do is a over 2t squared. This is a mistake that happens sometimes, okay? It's a mistake. You don't want it to happen to you. So yes, okay. Enough said. Good, we have that. We have v equals v0 plus acceleration times time, and then we have this v squared, v0 squared plus 2a x minus x0. So just about everything we need to solve for, we can use these three equations, so we have to become accustomed to using them. In the next chapter, chapter 3, after we learn about vectors, it will again be a repeat of these equations, so we're definitely going to get to know them. Okay, so those are the kinematic equations, and I want to do an example. You know, one of the homeworks was a bullet being fired through a board. This example is, what if you wanted to fire a bullet that would make it all the way to the moon, or make it to outer space? So suppose you had a cannon. In fact, there's an old science fiction thing where they launch some capsule out of a cannon here. So instead of a bullet, you can imagine there's a capsule in here with your passengers. Boom, launch it out to outer space. Possible, impossible, what's the problem here? Well, first we want to know, so this thing emerges here with some tremendous speed. There's actually a speed that, in the absence of wind resistance, would get you outside of the Earth's immediate gravity, which would get you to the moon. Okay. When we study gravity later on in the semester, we'll do this rigorously. Right now, I'm just going to put here v escape. So that's called the escape speed, is 11.2 kilometers per second. Okay. So we have the length of this cannon, and we want to know, find the acceleration given cannon of a certain length. If this were the science fiction cannon, you know, maybe it's the length of a couple football fields. Okay, it could be very long. So we won't plug in numbers initially, but what we'll see is acceleration, length, speed can be dealt with this equation right here. In this case, v sub 0 is going to be 0 because we're starting out at rest. Thing is being launched through here with some gigantic charge. So this will be 0, this will be our escape speed, and there's our acceleration. So let's do this in 2 steps. Use v squared equals v0 squared 2a x minus x0. And then we can say this initial speed is 0. And this is the length that we're talking about. And having set that up, we'll first get the formula, then we'll plug in some numbers and see what comes out. Okay, so now solve for A. Now solve for the acceleration. And what do we have? Acceleration equals v squared over 2L. That's the answer. So always do the algebra first. Even though I have that expression on the top in mind, still don't plug it in. Do the algebra first. This is a general expression. So now we'll do some examples. First example, we already know V, but it will be 1.12 times 10 to the 4 meters per second. So we convert it to meters per second. And let's say L is equal to 200 meters. That's the length of 2 football fields. Is that a lot or a little? Okay, let's see. Acceleration under these circumstances, we have 1.12 times 10 to the 4 meters per second squared divided by 2 times 200 meters. So it's meters squared per second squared divided by meters. That's the right units. Now I'm just going to estimate because I don't have a calculator here. But this is just about 1, so this is 10 to the 8 meters per second, meters squared per second squared. Well, actually, those are the final units. So it's 10 to the 8 divided by 400, 4 times 10 squared. So how much is that? That's 1/4 times 10 to the 6th equals 2.5 times 10 to the 5 meters per second squared. Okay, now we have to ask ourselves, what does that mean? So we just got a number out. So it's 0.25, 1/4, that was 0.25 times 10 to the 6. Okay, so 2.5 times 10 to the 5. Now, what do we compare a number like this to? See, a number has to be compared to another number to put it into perspective. And I'll just put here as a note, G is approximately, right, it's equal to 9.8, so it's approximately 10 to the 1 meters per second squared. So this is 25,000 times the acceleration due to gravity. As soon as we do dynamics, we'll realize that that acceleration would just crush you like a bug. Okay. The length of a football field is not, or 2 football fields is nothing for a problem like this. Okay. This is such a greater factor. So check acceleration that we found divided by G. Okay. By the way, do this kind of thing here. If you want to know these numbers better, use your calculator, but definitely go through with these things and figure them out for yourself. Now, I've mentioned it. This acceleration is so tremendous that as soon as you know dynamics, you realize it would just crush you. Okay. Good. So that's a good example. And you know, we had that homework problem coming up where the bullet goes through the board. We'll talk about that later. That's also just using this formula here. Okay, let's see how we're doing. Yeah, I'm gonna leave the formulas up there. And we'll do a little more constant acceleration, and we're gonna move into the next chapter. I actually set everything up last time in terms of free fall, but let's go ahead and do another free fall type of problem. So the example now is we have a vertical launch or a vertical throw, and here is our x-axis, something's being launched from the ground. It goes up, of course, and comes back down. So since being launched from the ground, we have x equals v0t minus a half gt squared. So vertical throw launched from the ground, good old x0 vanishes, acceleration is minus g. Okay, so there's our formula there. And we have the graph of this parabola. So anytime you don't have the initial condition, you can solve a lot just with without using the quadratic formula. So good. X is a function of t. Okay. Now the thing is, I've been saying we can answer any question about this thing. So I'll ask this question here. Question: how fast is the object moving? Okay. In other words, what is its speed when it reaches the maximum height divided by 2? When, and we'll write it this way, when x equals x maximum divided by 2. So what is the speed? So it basically, we're given a v sub 0. So note here, v sub 0 is given, and we want to know how fast the object is moving when x equals x max over 2. Okay, so there would be a couple of ways to discuss this here. We could say x max, so we could solve for the maximum height first. And that would bring us to this equation once again. If we want to find the maximum height, we have from v squared equals b squared, 0 squared minus 2g. Should I call x max or h? H. Okay. Maximum height is equal to h. Okay. So it comes to a stop there. So we have h is equal to, okay, now solving for h, where this went to 0, is equal to v0 squared over 2g. So that's the first part of the problem. That's the maximum height. What's the speed when it reaches half of that maximum height? So it's going to be an interesting one. There's always a couple ways to do these, because you can use the time, or just, you may not have to use the time. Okay. So we have x max divided by 2 is equal to 1/2 of this v0 squared over 2g. Remember, v0 is given, g is the natural constant. So now we know what the maximum height is divided by 2. How fast is the speed when something gets there? Okay. Now we can use this entire formula again. Use v squared equals v0 squared plus or minus 2g x minus x0, because now the height is x max over 2, and we can say v squared is equal to v0 squared minus 2g, and now we have to plug in this height here, and that's 1/2 v0 squared over 2g, make sure we don't lose anything there. So this is going to be really interesting. We have a 2 canceling, we have a g and a g. We're left with v0 squared divided by 2. So solving v squared equals v0 squared minus v0 squared divided by 2, because that's what was left here, so make sure you follow that. V squared is equal to v0 squared divided by 2. Take the square root of both sides. V equals plus or minus v0 divided by the square root of 2. And why the plus or minus? The plus or minus because it's on the way up and on the way down, okay? And in fact, the minus would be actually a velocity. So there's your answer, v0 divided by the square root of 2. The problem was how fast is the object moving when it's half of its maximum height. So halfway going up, halfway coming down. And it's not the speed divided by 2, it's the speed divided by the square root of 2. Okay, so that's an example. And again, if you write your notes out, leave a lot of space, you can put in some comments. You'll notice I didn't plug any numbers in until the very end, and the number I plugged in was 2. Okay, so this is a very general expression here. If you're interested, you could say, can I solve this problem using the first 2 equations? The answer would be yes, you can. It'll be probably a little more involved. Although not necessarily. This is the kind of thing you can do. Interesting problem, okay. Good. So as I said before, we will work with these quite a bit in chapter 3 again, so we haven't seen them for the last time. But this was an example. I just wanted to show you how you could think your way through a problem like this on the spot here. All right, checking our time again. We're going to, very nice. We're going to go into chapter 3 material now. Chapter 1 already has some of this. We want to talk about vector algebra. Vectors play a huge role in physics. In a sense, we've already been looking at them because of the plus and minus signs, but now we're going to do it carefully, formally. So I'll go ahead and erase everything. Start off with a new topic. And the vectors will be used a lot in chapter 3 and 4, and for the better part of the rest of the semester, several chapters. Come up again in physics 2b, so they're very important. Let's see here. Vectors. So what is a vector? A vector is a mathematical quantity with a direction and a magnitude. So the definition is that vectors indicate a direction and a magnitude. And you can think of arrows. Arrows point somewhere and they can have a length. So this is an arrow. It's pointing at the class right now, okay, pointing at the camera, pointing over at the ceiling. It has direction, pointing down, okay, pointing down, pointing up, okay. And the magnitude of this in terms of it being a length is exactly 1 meter. Okay. And this could be a vector as well, also pointing, and it would be, you know, about 1/10 of a meter. Okay, so there's different things there, but the arrows, the idea of them vectors being arrows is very useful. So direction and magnitude are arrows, and here I'll write vectors add like arrows. Now this is really a statement you should memorize, because with this statement, here I'll put it in scare quotes, you can reinvent, or you can invent the vector algebra right on the spot. So there's actually less to memorize than you think. The main thing to memorize, vectors add like arrows. Now how do arrows add? How do arrows add? You know, we actually have some, I'll bring them next time. We have some arrows, cardboard arrows with magnets on them, so we can actually place them on the blackboard, on the whiteboard. But I'll just do this. Say we have a vector of unit length pointing to the right, and we add a vector of unit length perpendicular to that one. Equals, I'll use 2 colors. This is what the addition of arrows means. Okay. You put the tail of one to the head of the other, the resultant, as it's called, the result of that addition is this diagonal arrow, okay? And speaking of this, so what is this resultant arrow? What is its length? You know, if we have 1 and 1, then we know the diagonal is just the square root of 2, diagonal across a square. So it has the length square root of 2, and it's pointing up at 45 degrees. And we could do, I'll say 2 units plus 1 unit equals, and I'll do the same thing. This time I'm going over 2 and up 1. That's where it points. And what is the length here? Okay. Now you have to use the Pythagorean Theorem. You have 2 squared is 4, plus 1 squared is 5, so that's the square root of 5. And now we have to say something about the angle, and we can say with theta, which gives its direction, theta being the inverse tangent of 1/2. And then the thing's been completely specified. One more example. And then I'll do a little of the formal vector algebra, but this business with the arrows is a good way to look at it. So suppose I have a vector of length 3, and I add a vector of length 1 that's pointing right opposite this first one. Okay. So what we have is 3 and 1 this way, and the resultant is 2. So that kind of reminds us of our football player problem that I just discussed up at the board here. Okay, because you can see that this vector could have been a displacement. This is a displacement in the other direction. The net displacement is the difference of these. So all 3 of these examples can be taken in arbitrary directions. So the vectors, you could say they live in 3-dimensional space, and you just add arrows to your heart's content. Good, so vectors add like arrows. So now I'll go a little more formal with this, just to give us the laws of vector algebra. So let's say here we have vector algebra. Now that we know how these things work, we have, let A, B be vectors, then we have A plus B equals B plus A. So the order that you add them doesn't matter. And the same thing is if we have A plus B, let's put a C into the mix here as well. So A plus B plus C is equal to A plus B plus C. So these are properties that you can just develop right out of what these things are geometrically. And A plus negative A is equal to 0, so the 0 can also be thought of as a vector. We won't even write that one down. Now we have components. So if we put a vector in a coordinate system, and the vector here is A, that's a Y, then we can talk about components of vectors as well. So let's go ahead and mark that there. Components. And so there's X and Y, and you can see that there would be an A sub X in a Cartesian coordinate system. We could have A equals A sub X plus A sub Y. If I think of these as vectors, I'll go ahead and do these red. We'd be coming across here, A sub X, A sub Y. And now I want to talk about the magnitude. As soon as we're in here, we've got our Pythagorean Theorem. So components for magnitude. So the magnitude of A, you say it's the vector with absolute value signs around it, because that's going to give the length. But what we also do is we say we can just write the letter without the arrow on top, and then that also represents the magnitude. And that is the square root of the magnitudes ax squared, ay squared, square root. Very clear here off of the geometry. And if I put an angle there, say with respect to the positive x-axis, I can also say, I'll just put here, also A sub x is A cosine theta, A sub y is equal to A sine theta. Again, just by the trigonometric definitions. Okay, so what we are going to do henceforth is refer to to draw the vector. We draw a lot of vectors in this class, right? We draw lots of arrows. So let's call this our convention. We draw the arrow and label it with its magnitude. Okay, we draw the arrow to indicate the direction and label it with its magnitude. Okay. And then, so that's the convention in a coordinate system. Say we have X and Y. If we draw the vector like this, okay, then in the coordinate system we'd give it a positive sign. If we draw it like this, then we'd still just label it, but since the arrow is pointing left in the coordinate system, we'd give it the negative sign. So in the coordinate system, put the sign direction in by hand, I'll say. And this is something we'll do a lot later, so don't worry about this convention too much right now, because I will use it continuously and I'll draw your attention to it. So good, that's our basics of vector algebra. And I think I'll just put a couple of examples on the homework. Let's see. I think at this stage, yeah, we have a few more minutes that I'll talk and then we'll put it in the homework. Okay, so I want to bring this discussion here, which we'll practice in the homework. No big deal, we'll do a lot of these. I want to bring it back to kinematics, because that's what's going on in chapter 3. So vector quantities exist in kinematics. So let's call this vectors in kinematics. Otherwise, I'll be leaving you hanging. So vectors in kinematics, let's just do our kinematic discussion here. Remember we had position, displacement, velocity, and acceleration. So right, we should always be able to just write these down. Well, position is clearly a vector, because if I want to give a position in this room somewhere and I have an origin, I have to point to that position. So position is a vector and it gets the letter R very often. So we're going to be calling the position vector R. And then the displacement vector is delta R, because it's the change of R. So I could say it's R minus R0. So that's an addition, right? The minus sign is plus the negative of a vector. And I talked about the negative directions of a vector. So we've got the displacement. The velocity v is a vector, is the delta R divided by delta t. And the acceleration is the delta v divided by delta t. Okay. So position, displacement, velocity, acceleration that we did in one dimension, they actually already were vectors. I kind of drew attention to it because of the positive and negative direction, but now they're explicitly vectors. And next time we're going to spend, we're going to do this thoroughly and see what these things mean. Let me just end with where we're headed with this. So what we're doing in chapter 3 is projectile motion. Instead of throwing things straight up and down, we're throwing them across the room. And that means instead of motion in a straight line, it's motion through space that really takes an arc shape. So next in chapter 3, after some more work with these, we launch something and it flies across the room in an arc. Okay. So imagine this is a tennis ball. What we're going to discover is at any instant in time, its position is a vector, and at any instant in time, its velocity is a vector. So this is an R vector, and this here is going to be a V vector, okay? And that's where we're headed with this. So next, just to give this a projectile motion. Good, let's see if we can find an assignment for us to get started on these vectors. There were There were some vectors in chapter 1 as well. Maybe we'll look at those. They're not as interesting. On the other hand, they were pretty thorough about it. So I'll call this homework 6. Just the homework is always listed along with the number of the lecture that we're in. And we'll just do a couple of vector problems, maybe from chapter 1 and chapter 3. $55 looks like the fun one. And always draw a picture on these. Draw a careful picture and it'll all make sense. And 63. 55 and 63. And let's see what chapter 3 has for us. Yeah, this is going to be a great chapter, actually. Actually, you know what? I'm going to put one more chapter 2 problem instead. The vectors we'll do next. Number 56 in chapter 2. So this is a rocket sled problem. I've solved a couple like this in the course of this lecture actually. So you're going to have to convert miles per hour to meters per second, okay? So note, miles per hour convert to meters per second, just so you can put it into perspective, because then we want to compare the rocket sled accelerations to g, just the way we did for our space capsule, okay? Okay, good. That's it for today. See you guys next time.